Hello together, my name is Ulrich Baehr and I'm presenting to you my paper for the day. So 1 second. It is called A New Method for Detecting Leaks in MEMS Accelerometers. So let's move this away. A new method for detecting leaks in MEMS accelerometers at Wafer-Level. So let's have a start. First of all, I'll give you a quick introduction into MEMS accelerometers. So normally a MEMS accelerometer consists of 3 parts. Basically the package in which the ASIC and the MEMS element is molded in. The MEMS element, of course, is there for detecting the acceleration itself, and the ASIC is there to make out of this detection a digital signal that can be used by some applications. The functionality of the acceleration sensor is, of course, within the MEMS element. We have a seismic mass that is connected with a spring to the rest of the MEMS, and it's moving due to external acceleration, can be vibration or car movements or something like this. And it has some capacity fingers that are connected to this seismic mass, and these capacity fingers are moving, of course, and so the distance between these fixed electrode fingers and these fingers is changing, and the capacity is changing as well, and this we can detect. So now, what is wafer-level test? Well, wafer-level test means that we are measuring the chips directly on the wafer. In this case, the MEMS itself. How is this done? Well, we have to use some probe or needle cards, like here on this right picture, that are used to actually connect to the pads of the MEMS elements. And the goal of this is, of course, that we can characterize the process as well as the design of new MEMS elements really fast and really early in development stage. And of course, it can be used in production where we want to check if chips are good and sort out the bad ones or even bad wafers. The idea is that we use electrical stimulation to detect non-electrical parameters like the sensitivity or the resonance frequency of the proof mass. In general, this means we have to find here something like less than 10,000 electrons somehow, or even detect changes in distance of lower than 1 nanometers. So we have to be very precise in a lot of things. Let's look at the next slide. So now the quality factor, which is of course a critical parameter for MEMS, is in this case used to determine the device's cavity pressure. And this cavity pressure is of course important because we can see if the device is leaky or not. If it's not leaky, this has to be in a certain cavity pressure range. If it gets a leak, then this pressure will change, and we can detect that. That's the whole idea, to find out if chips are leaky or not. The standard approach is to measure the resonance frequency and the damping via forced oscillation, which is called Q-factor method and is done widely in the industry, and is a very reliable method, of course. It brings its own problems though. One of the problems is that when you try to measure overdamped systems, you need kind of very high stimulus voltages to get anything moving in there, which makes sense, I guess. And therefore you see a shift in the measured frequency compared to the natural frequency, but also you see some effects like spring softening, which is referring to high electrical voltages softening the spring and moving or shifting the measured frequency even more downwards. Also, of course, you have small sensor movement. This means there's a precision loss and therefore a measurement time increase if you want to compensate for this precision. Well, our new approach there does something different. What we do is basically we measure the hysteresis between the sensor response and the stimulus voltage. And yeah, let's find out how we do this. So first of all, the platform we are using for this measurements, our digital measurement platform, consists of a digital processing system, which is basically an FPGA and PC for measurement control and also data acquisition. Then we have capacitive measurement, which we are doing with a carrier frequency method, which is applied with VHF here. And of course, for calibration, we need a reference capacitance where we know the capacitance very well. What we actually get then on the electrodes of our, of our DOT is a combination of our test voltage, which is there to excite the DOT, and our carrier voltage. And this is called V in, which is shown here in this equation. And this is connected to either C1 or C2 to excite and measure the sensor. The capacitance then can be calculated from the V out signal coming out here, and of course the calibration factor. So now to our stimulus signal that we are using to find out what our damping is. So what we're using is a ramp function where we ramp up the sensor up to about 80% of the pull-in voltage, and from there we're going down into the negative and back up again. Of course, when we go into the negative, because the actual force is the square of the voltage, we see that the sensor moving in the same direction. So what you see here in black is basically the response of the sensor, the capacity. We can configure the gradient, of course. This means this gradient could be faster or slower, depending if you want to have a very fast measurement or a very accurate measurement. And if we have a look now at this small window of the measurement, which we do in the next slide, we can see that when our stimulus voltage reaches the maximum, our sensor is not at its maximum yet. It takes till this timestamp T2 till the sensor with its capacitance also at its maximum. And this delayed response is a very good estimator for the specific damping of the device. So we have to find a method somehow to estimate this timing delay as accurate as possible. And that's what we're trying to do. The curve till there can be fit with a fourth order fit, which is important for seeing how this method works. So if we now look at the CV diagram of our measurement, we see up here is the stimulus voltage on the x-axis and the capacitance on the y-axis. You can see that the measurement points are divided between the ramp up and the ramp down of this ramp stimulus. And you can fit both of these points with different x of 4 fits. It's just polynomial fits. And what you can do then is calculate the enclosed area between that, which is basically the response of the sensor, right? And you can do that very time efficiently with the fit coefficients. You have to do it though for both electrodes. So this would be only one electrode. You have to do it for both to basically compensate for the raw offset of the sensor. And the result is called hysteresis area, or d-hys in this paper. So if we compare now in the model D versus d-hys, we can see that the biggest factor here is the gradient of the ramp stimulus, how fast we do the ramp up. If you do the ramp up really slow, like in this black line, we see there's a nearly perfect correlation between the damping and the hys. If you do it really fast, well, we get a really nice response from the hys. It's changing much over the damping, but it's not that perfect anymore. You see the actual points, they're not linear anymore. So there's some optimum in between, as always, and it depends largely on which device you actually want to measure. When we compare the test methods, we did the following. We took a wafer and made about 4% of the chips intentionally leaky, so we can detect that. And what we saw from the results here on this wafer maps, you can see with the pure eye that both methods are able to detect the leaky chips. For the Q factor method up here, you see that the leaky chips are these two clouds. For the hys method, you see the same clouds at the same positions. What you can also see is that there's a bit more noise at the baseline for the hys, but the leaky chips have a way smaller standard deviation than for the Q factor method. And also the difference between leaky and non-leaky chips is 22% larger. So it makes it easier to define a limit here to cut out these bad chips in this example. Well, now for the test time. We checked the test time for 3 different sensor types with 5,000 devices each. And what we found is that basically the pull-in voltage of the device and the gradient play the biggest role for the measurement time of the hys. But if we compare this to the conventional method, you see that even for the worst sensor and a very conservative KR configuration, we get speed up factors between 6.1 and 8.8. If we go for the most aggressive KR configuration and for the best sensor type, we get even up to a factor of 13. So we save a lot of time here. So, well, that's it already. In the conclusion, well, we introduced a new method for detecting leaky MEMS accelerometers. The delayed response of the MEMS is basically evaluated for the damping estimation. That's the trick here. And the test and simulation results show very good correlation to the Q-factor method. This is why we can actually use it. And the better precision for the highly damped devices is one of the main motivations. So we have something we can use for highly damped devices to detect leaky chips, which was kind of difficult before, I have to say. Also, we can save a lot of measurement time, which is probably the most important part because, as you all know, in mass production, time is money. So, thank you for that. We're going back to this build. So thank you for listening to me. And yeah, I hope you have interesting questions.